Hi everyone, here I want to introduce the full stack observability and high concurrency system and monitoring we've implemented for this Exchange project. We'll divide this into three topics. The first part introduces the standardized SDK I designed, which provides three functions. First, it works out of the box. Once a new service references it without configuration or code, its metric data can automatically be displayed on the dashboard in Grafana. The second part is metric governance. If every developer uses their own method for naming metrics and tags, it becomes extremely painful to perform aggregate queries on Grafana. Moreover, for managers, handling all the metric acquisition points in the system would become quite complex. Therefore, I designed a solution within this standardized SDK. The third part is high-performance encapsulation, because Micrometer itself is relatively slow in querying and registering metrics internally. In our system, which handles tens of thousands of TPS per second, not optimizing would create a significant performance bottleneck. So we've encapsulated the 5 main metric objects of Micrometer here. And besides performance optimization, it also provides some fake data. The API facade conducts checks to ensure that when developers set up metric acquisition points, they must comply with our established standards. It also eliminates some boilerplate code. The second part is the systematic observability of business and performance. For the business part, besides measuring the QPS of orders, it also categorizes by status, such as success, failure, or duplicate, etc. So, when there's an issue with an order, we can quickly pinpoint which part of the order process the problem might be based on the distribution of its status. We also measure the TPS of matching, as well as tail latency and average latency, precisely quantifying the entire system's performance, throughput and responsiveness under high load. We have also conducted in-depth metric collection for some key components. For example, in the matching engine's thread pool, metrics have been acquired to observe its queue depth, active threads and thread saturation. This helps during stress testing to pinpoint details such as the task queue in the thread pool not processing quickly enough. The third part introduces its value. All these performance monitors help with bottleneck analysis in load testing and system capacity planning. And for risk control and other purposes, it provides a core data foundation. Finally, I'll introduce the overall architecture and vision. In the distributed system running on the K8s cluster, besides the monitoring metrics mentioned earlier, we can also monitor node and pod metrics and even other server metrics. These monitoring metrics help us when a failure occurs. We receive alerts immediately and can quickly locate which part the issue is in based on the systemic metric data. An exceptional development experience. First, I'd like to emphasize that the core value of this monitoring SDK is that it offers an out-of-the-box exceptional development experience. I've designed it as a standard Spring Boot starter, meaning any microservice in our team only needs to introduce this dependency in Maven. No initialization code needs to be written, and the system will automatically complete the underlying meta register configuration and inject common environment labels, such as app, eBay labels, and automatically enables Prometheus metric endpoints. This zero configuration design means once a new service starts, its health and business metrics automatically appear on the Grafana dashboard, greatly enhancing our team's development and operational efficiency. Now let's take a look at Grafana. The Exchange account service metrics are already integrated. All right, now let's take a look at the code. The configuration for the Exchange account project, there is no configuration related to Prometheus in its setup. Its configuration is actually minimal, and the reason it can be simplified is that most of its infrastructure has been encapsulated and modularized through the SDK. Let's take another look at its modules. Its dependencies, the dependency part is actually very clean as well. Regarding monitoring related dependencies, it actually does not introduce Prometheus related dependencies. It only introduces this one SDK core module. All right, now let's look at what kind of monitoring functions the SDK core module provides. Firstly, it provides some components related to metrics, which I will explain shortly. The second part is that it provides unified configuration management. In this configuration, all the configurations related to Prometheus are set here. This has two benefits. The first is that the configurations of all microservices are managed uniformly. As long as you modify this place, all microservices will be updated accordingly. The second part is that if a microservice has some special configurations, you can set them within the microservice, and they can be attached here to override the existing configurations. It provides some flexibility in configuration. This configuration is actually achieved through a special mechanism. This effect is implemented this way, and you can take another look at the code here. The second part it provides is dependency management. All the dependencies related to Prometheus monitoring configurations are managed here uniformly and can be imported through this module to automatically introduce them into each service. That's the main point here. Of course, creating this SDK is also to address a long-standing pain point in microservice architecture, which is metric governance. If each service were to handle its own metrics, we would quickly face chaos in metric naming, issues with inconsistent label definitions. For example, some people use service name for labels, while others use app name, which makes Grafana's aggregated queries very painful. Moreover, without unified management, tracking all the monitoring point codes and understanding exactly what is being monitored becomes quite complicated. Therefore, I enforced a strict standard through the SDK, leveraging Java's features to design a unified exchange metric management class. So when developers add instrumentation, they don't need to enter anything manually. They simply reference the dependencies. This not only eliminates spelling errors, but also enforces a mandatory standardization of all metric naming structures. And the necessary tags, if any are missing, they will be checked and trigger an error. This lays a solid data foundation for subsequent full link interfaces. All right, now let's look at the metrics for the order service. It has this exchange order request metric. Then let's look at the code in the common SDK module. This class manages all the metric monitoring for the Exchange project. Then, to explain here, for this metric, its name is the name of the metric itself. Micrometer will automatically convert the dots in the name into camel case format. The second parameter in the code here indicates which labels are mandatory for this metric, and if any are missing, it will result in an error. Then let's take a look at the labels here. The labels side, status, and symbol are mandatory. The labels app and email are automatically added by the SDK core management. The benefit of this is that managers only need to set the standard name and necessary labels for all metrics uniformly here. All developers must adhere to and follow this strictly. As for how the label checking is done, you can trace it. From here, you can start tracing deeper into the code. The second advantage of this is that when we want to know exactly where the metrics are embedded in the project, we just need to trace it here to find out all the points we've embedded. For example, here we have the order request, matching delay, and transaction statistics information. I want to look at the metric for placing an order, just trace it. You can also easily see the invocations from the calling side. This is a software within the SDK for monitoring, a unified software related to monitoring. I will explain it in a moment. The first parameter is the sound wave we just mentioned, and the following parameters are: just place it here and follow these 3 tags. Input the 3 tags accordingly, and that will do. Let's first introduce the third part, high performance encapsulation. I've encapsulated 5 commonly used Micrometer metric objects in the SDK core. Since retrieving metrics internally with Micrometer is actually quite slow, in high-frequency paths like matching engines, which process tens of thousands of operations per second, if we perform metric searches or registrations for every single buy point, it would create a lot of unnecessary object allocations and machine stress. Through encapsulation with caching mechanisms, we can directly retrieve existing metrics from the cache and start statistics. This ensures that we obtain high-precision monitoring data while almost not affecting the latency of the business system. This is a crucial design for trading systems that pursue ultimate performance. And these encapsulations also provide mandatory adherence to the labeling specifications of Iran with fake edit, faked facade checks. Let's take a look at the SDK core module first. In this package path, 5 commonly used Micrometer metric objects are encapsulated here. Let's take a look at the encapsulation of the temp timer. Here you can see it has implemented the cache part we just mentioned. So if the user wants to use it, the scenario would look like this. This is a static method, so it's used directly like this. This is the user's business logic. He only needs to call this static method, supply the metric, then inject the business logic using a runnable, and finally append the tag he wants to add. This way, a metric collection is completed. Then internally, this method will check whether it's in long and comply with our specifications. And it will retrieve the metric within the metrics, obtain the metric object from the cache, and perform the recording action. Basically, these 5 objects are all encapsulated similarly, and we try to use a static approach to make usage simpler. Okay, next let's talk about business and performance monitoring. Besides standard CPU and memory monitoring, I focus the monitoring on key business metrics and the deep correlation with the performance of key components. Taking the core trading link of an exchange as an example, I implemented monitoring in the following dimensions. The first is the QPS, queries per second of order flow, and it is distributed according to status. This way, we monitor not only the request volume, but also the processing status of orders. This allows us to promptly identify whether order anomalies are due to the triggering of specific risk control rules. The anomalies caused or other phenomena can all be revealed. The second is the performance of the matching engine. We implemented TPS, transactions per second, for matching count per second, and delay monitoring accurate to microseconds. We not only look at average latency, but also pay more attention to the maximum latency. This is crucial for identifying the long tail effect in the matching process. The third part involves deep monitoring of the saturation level of the execution thread pool. For execution sequences in multi-thread pools, monitoring is very important. For single-thread execution sequence models in the matching engine, we deeply monitored the depth and active status of their task queues. During stress testing, does this help us identify whether the latency increase is due to insufficient CPU? Or is it due to the accumulation of tasks for specific trading pairs in the multi-threaded queue? In such scenarios, this is useful. In addition, for system integrity, we have also planned monitoring for the rate of change in single account assets. This is, in my view, a core metric for improving cash flow transparency. By observing the rate of change in account balances, we can promptly identify potential abnormal transactions and risk control issues. This will be a crucial step in the next phase of strengthening our system's self-audit capabilities. Well, based on this standardized toolset, we have implemented full link observation capabilities from business to system. This is crucial for performance stress testing and average analysis of high concurrency systems. This deep observation capability transforms monitoring from being a passive alarm system to a core basis for optimizing system performance and conducting capacity planning. This demonstrates that our monitoring system is capable of going from business phenomena directly down to the code and execution sequence levels. Now let's take a look at the metrics I've set for this system. The one above is a business metric and the one below is a system metric. These two are Kafka dashboards. You can find the JSON templates in this project's design folder under the matching service. You can locate these two JSON files there and import them. Let's first look at the system monitoring part. This monitoring uses the standard 4701, the classic Zabbix monitoring dashboard. It supports both multiple and single service selection, and you can also choose which specific instance you want to view. In addition to basic information and I/O data, this dashboard provides JVM records, an overview of memory, and some system information of JBA itself. It also details heap memory and off-heap memory. It contains detailed information, including GC frequency, pause time, and object production rate, among others. And that's about it. For our River engine, we should focus primarily on the GC aspect, particularly the object production rate. Is it too fast? And is the GC pause time and frequency too long? The third point of concern is the heap. For each object from the Eden space to being promoted to the survivor space, is the promotion speed too fast? If so, this is an area where we need to continue optimizing. As for the business part, this is where let me see. Here, as we just mentioned, I have categorized the QQPS of orders into statuses: successful, failed, or duplicate orders. Any new status will be displayed. This one refers to the TPS, the number of transactions matched per second. And this is for Trading Team 1001, where you can select the symbol. This is the processing delay of the matching engine with average and maximum delay. This delay statistic is because my matching engine processes a batch of information at a time. So this statistic is the processing time for each batch. The higher values seen here are because in the development environment, due to memory constraints, I have minimized all server memory performance requirements and even disabled some code optimizations. So sometimes there's higher latency, right, when it starts executing. However, normally it should be very low, like this 2 milliseconds, or even lower. The last part is monitoring the thread pool, specifically for the search engine's thread pool. This is because it's a single-threaded model, so each trading queue has its own dedicated thread. And each runs only one execution sequence. So for 1001, the pool size is 1, and its active thread is also 1. Then, the number of tasks currently queued for each thread is displayed here. And this is the saturation level of the thread pool. Thread saturation refers to in the 60 seconds allocated by the CPU, how many seconds your thread has run. The proportion allocated is, for example, if you're given 60 seconds and you actually use a certain number of seconds, that's your saturation. So suppose you're given 60 CPU seconds and you use all 60 seconds, then this. Let's talk about the final part, and below is the overall architecture diagram of everything we've just discussed. Although the current project mainly focuses on application layer monitoring, I have a clear plan for the observability of the entire site. In the future production environment, I plan to introduce Node Exporter and Kubernetes metric server to collect the underlying metrics of pods and nodes. This will give us the ability to vertically correlate business anomalies to infrastructure bottlenecks. For example, in a real scenario, when the business dashboard shows that the offloading engine latency is surging, we can immediately drill down to the pod level to confirm whether it's due to improper memory limit settings causing frequent GC. We can even proactively prevent kills. Or we can observe disk I/O bottlenecks at the node level to see if they affect the write speed of WAL. This end-to-end monitoring perspective can significantly reduce the average time to repair failures, NTTR. And it provides precise data integration for subsequent system scaling and resource planning.